Okay, an extra curve sketching example here. This one follows a lot of the same steps, but it's just a little bit weird in how it's made up. So just to cover one of the weird examples, and you're going to see a lot of weird examples in the homework, but just to cover one of the weird examples, we go after this one. So follow the same steps that I had indicated before. We start with domain. And here there's no denominator to worry about. So there's no asymptotes to worry about. But this is a new look, is that it's got a square root in it. And the square root brings up its own kind of domain issues in that we can't take square root of negative numbers in our real number system. So what that means is when we look at the domain, what we really need is for x squared minus 4 to be greater than or equal to 0 if we're going to have numbers in our domain. Now, at first glance, that looks like big trouble to try and analyze that situation. But if we factor this thing into x plus 2, x minus 2, we can immediately go after one of our old friends, which is just to build one of these tables to find out when does x plus 2, x minus 2, when is it greater than or equal to 0? And so our important numbers here are x equals negative 2 and positive 2. So we're going to build a little table here and go, okay, what's happening before negative 2? What's happening between negative 2 and 2? And what's happening when x is greater than 2? And we're just looking at x squared minus 4 equal to x plus 2, x minus 2. And if we look less than negative 2, say negative 5, both those factors will be negative, so we get a positive value there. Between negative 2 and 2, of course, we use 0, so we'll get a positive and a negative, so we get negative in there. And then x greater than 2, say like 10, both those factors will be positive, so we get positive in here. Now let's just make sure we remember what we're looking for here. For our domain to exist, we need x squared minus 4 to be greater than or equal to 0, so that's here and here. So our domain of this function is x element of reals such that x is less than negative 2, union x greater than 2. I mean, maybe you haven't seen that union symbol before, and so you could write and in there if you want, or with, however you want. But the important thing to recognize here is that those are the only two sections that this function can exist in. That's very strange. And so we're going to have to do some analysis along the way. And once you see the result, once you see the graph, it'll go, oh, okay, well, that's all you got to do. So right now it seems a little bit mysterious. So we'll get to dealing with all that. So then we want intercepts. That was the second category of stuff we're going to look at. So for y-intercept, set x equal to 0. And so I get y equals square root negative 4. So no y-intercept. You can't do the square root of negative 4. Maybe we should have seen that coming. If the domain does not exist between negative 2 and 2, like if there's no x values allowed between negative 2 and 2, then of course there's going to be no y-intercept. But here, we reconfirmed that here. And then so for x-intercept, set y equal to 0, so I get 0 equals square root of x squared minus 4. So I get 0 equals x squared minus 4. So I get x equals negative 2 or x equals positive 2. Those are my two x-intercepts. So that's good. That's going to be a good start for our graph. Now, in other sections, we looked at asymptotes. But without any denominator here, we don't have any asymptotes, so no asymptotes to worry about here. So we switch over to intervals of increase and decrease. And this is another way in which this function is a little bit different than ones we've looked at before, because the function itself is a square root, so I got square root x squared minus 4, and finding derivatives of square roots has its own special challenges. So we're going to go f at x equals x squared minus 4 to the 1/2, and then we can go f prime at x equals 1/2 x squared minus 4 to the negative 1/2, but chain rule, multiplied by the derivative of the inside, I get a little 2x in there. So then, simplify that down, f prime at x. I'm going to get 2x over 2 root x squared minus 4. And, you know, it's interesting that this chapter is really nice because it shows off why we simplify the derivatives like we do. We simplify them like we do so we can get down to nice things like this that can be analyzed and used. So what I end up with is x over root x squared minus 4. And while this function is very different looking than previous functions, the steps are still the same for critical numbers. Set f prime at x equal to 0. So what I really want is the numerator equal to 0, and I get x equals 0. Now, here's what's interesting here. That x equals 0 is a critical number, and yet it's not in the domain. So that is very strange. I mean, there's got to be something more to this story, and there really is as we go into complex numbers in much later courses. For now, we just leave that as is and go, well, okay, we don't have to worry about it if it's not in the domain. So we do have to still build our interval chart for our different sections where this thing exists. We still want to know what's happening when x is less than -2, and I'm going to put this in here, even though it's a really silly thing to do, to put that in there because it doesn't exist. That's all I'm going to do is I'm going to write in there just to make it clear. I get x over root x squared minus 4. So I want to look before I get to -2, and I want to look between -2 and 2 and after 2. But in here, it does not exist. The function doesn't exist. So we're not going to really do anything in there because nothing's going on in there, whatever that means. I mean, right now it seems like a bit of a mystery. So for x less than -2, the numerator is going to be negative, and the denominator is going to be positive. Because let's say we put like a -3 in there, that denominator comes out to square root of 9 minus 4, which is positive. So, okay, so negative, so this is decreasing. So we still are getting information here. The function must be decreasing into -2. And for x greater than 2, we'll get positive on the top and positive on the bottom. So this is positive. So this is increasing in there. So we're decreasing up to -2, increasing out of +2 and not existing in between. So really no max or min that we can see here. And you might think, well, it does go decreasing, increasing. Well, yeah, but to be a min, it would have to decrease up to a point and then increase out of that point, and that's not what happened here. It happens here. It jumps through. And so if that seems a little strange, well, that's okay. It can all seem a little strange. When you see the graph, it may come together a little bit about how this all plays out. So, do I have room down here? Oh, yeah, I've got some room down here. So now, what was my derivative I had left there? I had f prime at x is x over root x squared minus 4. What am I after here? I'm going after concavity now. So, well, that's not a very good form for this to do the derivative in. And you have some choices here about how you write this up. I like the quotient rule. Other people like to stick with the product rule, and so either way is good. So I'll show the quotient rule here to just tidy this up before I get ready. This is going to be x over x, just tidy that up for x squared minus 4, and that's all to the 1/2. So now I go double derivative, and we'll just go slow here to make sure we get this down. Derivative of the top times the bottom minus the derivative of the bottom, and then a little chain rule on the bottom, times the top, all over the bottom squared. So if it's x squared minus 4 to the 1/2 squared, I actually get x squared minus 4 now in the bottom there. Okay, so now, some simplification. The same steps as before. We really want to deal and make sure our monomial is as good as we can get so we can get the best possible common factor out of this. So negative 1/2 times 2x, I get a negative 2x times x. Multiply those all together, I get negative x squared, and I've still got this scary looking x squared minus 4 to the negative 1/2, and in the bottom, x squared minus 4. All right. go to tidy that up a little bit. Now, to common factor out of this mess, and maybe to see the common factor a little better, I'll bring these brackets back that were here before, is there's as an x squared minus 4 common factor. And how many x squared minus 4s? Well, that's awkward because we're sort of used to common factors being all positive numbers here, but here I've got a 1 as the exponent on the first x squared minus 4. That's not right. Derivative of the top times the bottom. That's got a 1/2 on there. That's why it's so weird looking. Okay, so x squared minus 4 to the 1/2, x squared minus 4 to the negative 1/2. And so now the common factor is the lowest power of x. And the lowest power of x here is the negative 1/2. And so what's left in the brackets is 1 power of x squared minus 4. Because negative 1/2 plus 1 would be the 1/2 that I need there. And then the x squared there. How nice does that come out? So when you choose the exact right common factor in these situations, that inside the square brackets comes out so nicely. And that's why we did such crazy practice on derivatives before coming to this chapter. And so I'm going to tidy up what's in the brackets. And I get a nice little negative 4 there. Isn't that nice? And down here I get x squared minus 4 to the 1/2. There was already an x squared minus 4. And so this ends up as f double prime at x equals negative 4 over x squared minus 4, but now to the 3/2. And maybe we want to even fix that up a little bit more from there. I'll go over here. F double prime at x equals negative 4 over square root x squared minus 4 cubed. There's several ways to write that, depending on how you want it to look. But that would be the most formal way, I think. So when we want to do the concavity here, we're looking for when does this double derivative come out to be 0. And since the numerator is negative 4, this is never equal 0. So we're right back to that same chart we built before. X less than negative 2, between negative 2 and 2, and x greater than 2. We're just using the domain now to investigate the concavity. And so I'm just going to write f double prime at x here. So if I take a negative 2, like a negative 3 and put it in that thing, the numerator is going to be negative, denominator is going to be positive. So this thing comes out to be negative. So this is concave down. In here does not exist. And over here, x greater than 2, say like 10, we get negative and positive. And so this is also negative. So this is also concave down. And like I said before, this concavity thing really is just the icing on the cake. It really tells you, here's what the shape of the graph's going to look like. And that can make you feel real good when you go to do your graph. So here I go, ready to do my graph. And this is all pretty mysterious. You're going to be surprised how simple this all works out based on the evidence that's given. So let me just use the evidence to try and draw the graph. So sometimes when you do all this procedure, you do diamc and you go all the way through it, you feel like, oh, do I have enough information to graph this thing? And then you just put it on a graph, the pieces you have, and it comes out to be really good. So, so we know the domain, less than negative 2 and x greater than 2. And so we found no y-intercept. We had an x-intercept at negative 2. I'm going to switch to that other blue color. I like how that looks on the screen here. So negative 2 and positive 2. And then intervals of increase and decrease. So let's go to that interval chart. It's decreasing all the way up to negative 2. So it must be coming in and decreasing all the way into negative 2 like that. And then after 2, it increases coming out of there. And you see, there's the domain. No x values, nothing to draw between negative 2 and 2. And then the icing on the cake is the concavity. It says concave down for x less than negative 2. That's what I have, is it bending downwards. And then for x greater than 2, it's concave down as well. So the concavity is just assurance that this graph doesn't turn the other way or even out. You're wondering, does it come back down? Does it loop back up? We never really could decide in advanced functions if it had little shapes that we couldn't get or understand with the information we had. But here, with the concavity information there, we know it's just concave down on both sides, so we know that this is the right shape of the graph, and we've got the right increasing, decreasing. Now, how far and fast does it go up? Well, there's no way to tell that from what we did here. If you really wanted individual points, you could sub in some x values and use that to frame the y values here. The important thing is it's decreasing all the way into -2 and increasing out, and doesn't exist in between. Hopefully that helps you to have a little faith when you're dealing with weird situations. It's just to follow the procedure that we've outlined here. DIAMC. Let me just highlight that. I went domain, intercepts, asymptotes, intervals of increase and decrease. And from that, I got max min, and then concavity. And use all of those pieces of evidence to draw the graph. So after that example, there's another one. 18, and this is a lot like other ones that we've already seen. It's got a numerator and a denominator, so it'll allow you to do all the pieces. The solution to that will be on the webpage. So I encourage you to go and try this one right now. You know, this is the one to go, and now here's your chance to go try one all by yourself and get as far as you can, do all the pieces you can, all the things that you can figure out, and put it on the graph there as best you can, and then check the solutions and go, okay, where am I at? How am I doing with all this? How much did I remember? How much could I do? And, you know, don't worry too much if it's pretty good or pretty bad. You know, like if it's pretty good, you can feel pretty confident. If it doesn't go very well, that's all right. You're just getting used to it. And then, boy, there's lots more for you to practice there. And if you have trouble with the practice ones, you know, those first 4, they really start you off with 4 sort of tough ones. I sort of encourage, the way I've taught it here, to start at 5. 9 shouldn't be a big problem. 11 shouldn't be a big problem. 13, you know, those type of ones might be good ones to start off with, and then come back to the other ones as you get going, because some of them have some special cases in here. And ones like this one, number 3, square root of x plus 5, you might already know how to graph that in other ways, but try and use these methods on an easy one like that to get these methods down pat. Okay, give it a run. It'll take a little bit of practice, but you'll get going on it.